Good morning everyone, I'm Ivan, we are Capstone Group 12 and we are excited to show you what we have achieved for Capstone so far. Here is our team and we are fortunate to have DSCA as our industry partner company. Just to recap, we started with a very open problem statement and we narrowed it down by looking at the disaster sites, identifying the challenges it involved. We also conducted the study to understand the stages of search and rescue and we identified that the reconnaissance stage being the most crucial. On top of that, we also did a stakeholder analysis to understand the personnel involved. With all of the information that we have, we created the household quality matrix and identified 6 important functional requirements for our projects. But also considering our constraints that we have, we narrowed down our scope to only operate 1 drone, but simulate multiple drones working together and each carrying 1 detection mechanism. With all of that, this is our refined problem statement, which is how might we optimize the search and rescue process in a disaster scenario using human-drone collaboration for enhanced target detection over versatile terrain. To also elaborate a bit, what we meant by guided autonomy here is that the human has to give a goal to the robot, but the robot has to autonomously decide the steps it takes to achieve that goal. From all of that, we will give you an overview of our project, and this is how it looks like. We have the mission control, the sensor, and how you all integrate together with the drones. I'll pass my time to Paulong to take you through our mission control.
Thanks, Ivan. So we first start with planning. How can the drone know where to search given the user input of the hotspot? We do this by basing on metric like guarantee capture or medium time capture. So we decompose the planning problem into 3 subtasks: clustering of the hotspots, assigning drone to the cluster, and finally, drone searching within the cluster. For clustering, we have child algorithm like the density by clustering, which add on hotspot 1 by 1, and also the hierarchical Dyna, which breaking down large cluster into smaller but manageable search area. We chose Dyna because they have consistent performance with increasing number of hotspots. Next, for task assignment, the drone will prioritize the cluster with the most hotspots. This is a simple matrix-based method instead of random or probabilistic one. For searching, we're focusing on the naive or adaptive traversal and didn't try out reinforcement learning because the first 2 methods have shown very promising results. As you can see, on the left-hand side, for naive traversal, the drone will simply do an outward spiral. This will go for guarantee capture by covering all the cells, while for adaptive traversal, the drone will aim for the area with the highest probability, aiming for medium time capture. With that, we have achieved our first checkpoint, scalability to larger area using our search algorithm. Next question will show how we iterate everything together into our mission control.
Thank you, Paulong. I'll be sharing about our mission control, which is essentially the user interface the drone operator has with the MASNRD system. So what does it do? The drone operator can input hotspots, which are objectives for the MASNRD system to search, and it allows you to define clusterings, do assignment, and also execute emergency drone actions, as well as real-time drone monitoring. So this is the user journey that the user has when they interact with MASNRD. First, they input hotspots, and then the MASNRD system will cluster these hotspots. The user would then confirm clustering before assigning these drones to do independent search over these clusters. The drones will also feedback back to the UI whenever it finds a victim and conducts the search independently. So these are the features that our mission control has. It allows for real-time monitoring and emergency takeover whenever there's issues with the drone. This includes landing and disconnecting to the drone. You can also have expert input of hotspots, which will be then smartly clustered together in neighboring hotspots will be clustered together, and then it'll be assigned in a priority queue to different drones before doing a probabilistic search over these clusters. So this is a demonstration of the user interface and how the drone operator can use it. So as you can see, the drones are being dispatched to these different clusters, and over these paths, the drones would then search, and as you can see, the markers at the place where the victims are detected are shown here on the map. And now I'll pass the time to so now we've achieved remote operation and guided autonomy. Now I'll pass the time to Axel, who will be sharing about sensing.
Thank you, Waishan. So our sensor is designed to detect RF signals based on the following design criteria: range, permeability, field of view, response time and battery consumption. Okay. Based on our literature review, we have identified existing solutions used in search and rescue missions and weighed it against several design requirements. Eventually, we settled on radio as it was most suitable for our project. With our radio sensor, we are able to detect RF signals propagating through concrete walls and can even operate in low light conditions too. Also, it has a much lower power consumption compared to the other technologies that we have researched. Here we have a table showcasing all 4 of our prototypes. Our latest addition is our final prototype, which detects and quantifies the RSSI of most RF signal sources across a wider frequency spectrum. It also comes equipped with a directional waveguide and is capable of FFT for signal processing. However, it is slightly heavier compared to the other prototypes we have developed. So here is a close-up of our final prototype. It consists of a 2.4 GHz antenna to sample RF signals for processing by the HAC RF1 SDR. It comes with the waveguide to direct RF signals towards the receiving antenna. And we have the SDR here to process the RF signals for using the fast Fourier transform algorithm for discrimination by the onboard computer. An access point is paired with the sensor to spoof known access points within the disaster region. Because any mobile device with their Wi-Fi settings turned on will automatically begin to connect to known access points. Hence, we can force a more consistent transmission of packets between connected mobile devices and the access point to be more easily detected by the sensor. Next, the onboard computer takes the FFT process signals from the SDR to identify active communication channels. It uses unsupervised machine learning methods and a technique called the HDB scan. So this is a table documenting the test results of all 4 of our prototypes. We chose the final prototype for use on our drones due to its superior performance and characteristics. Hence, the final prototype meets the proposed functionalities of low light operation and detection accuracy. Now pass my time over to Ryan.
Thanks, Axel. Now, I'll give you guys a bird's eye view of our entire system. So the middleware is the brain of the drone. It communicates with the flight controller to get GPS coordinates, hands it over to the path planner to compute path planning information. This path planning information is then handed back to the flight controller to tell the drone where to actually go. In terms of detection, when the RF signal detects a signal, it passes it over to the middleware, which hands it over to the mission control. So the mission control is consisting of 3 main components. The server arbitrates information exchange between users and the drones, while handling all necessary clustering and task assignment, while keeping the user in the loop. In terms of firmware, our flight controller runs the PX4 flight stack, which can be controlled through remote control, mission control firmware like Q-gun control, or an onboard computer running ROS2. The last one is how we control the drone. Putting these together, we still need some way to effectively test our system in a controlled environment. We use Gazebo, importing in a bare bones model of the SUTD field from Blender. With Gazebo, we can simulate a flight controller, allowing us to effectively test our software in varying environments. In the next slide, I'll show how the user journey can be replicated in our simulation. So first, the user enters several hotspots as shown here. The mission control computes the clustering and distributes these tasks to the drone. Then the drones will autonomously travel to the start points and begin conducting their own search operations. Over here you see an exhaustive spiral search. Its mode and potential and estimated connectivity are all reflected here in the GUI. In the event of an emergency, the user can still conduct emergency landings and all that. So by testing the drone in the drone arena and in various environments in Gazebo, we can hence enable efficient testing in various terrains. Now I'll pass my time over to Kobe.
Alright, thanks Ryan. Now that we've seen the simulation, we'll be looking through the real-world implementation. So this is the layout plan for our showcase and testing. We will be flying the drone around in the aerial arena with phones lying around on the floor here. At level 7, our main operator will operate the mission control and will also connect the RTK base station there. For safety reasons, we'll have a drone operator on ground have emergency takeovers. To power our drone, we'll be using a 10,000 milliamp hour battery and we'll be using the existing drone power system to power both the drone and the onboard computer. For the onboard computer, we'll be stepping down the power to 5 volts, and we'll also be powering the RF sensor through the onboard computer. The drone has several communication devices. First is the real-time kinematics for localizations, and for communication with the mission control, we'll be using 5 GHz Wi-Fi, and we'll also be using a 2.4 GHz Wi-Fi for our AP, which tries to create a connection with the phone. Now I'll pass the time to Daniel to talk about our results.
Okay, so thank you, Corvio. So now I'm discussing some of the existing solutions with respect to the mission planning capabilities. So one of the existing solutions is actually called Q-ground control. So what you see here is actually the waypoints, the planned waypoints. And the one in green is actually the targeted waypoint, so it's where it's supposed to move. And the one in red is actually the heading, or the GPS heading, or where it's supposed to face. So what's the problem with this is that it requires the operator to actually input a lot of different waypoints. And in a search and rescue mission, time is of the essence, and we need to ensure that we can do it like instantaneously. So this capability is sort of not available because the disaster situation is always changing, and we cannot like instantaneously accommodate to that. One of the issues is that there is also inaccurate GPS estimate. So this can be perhaps understand from the telemetry communications. So it's using a 915 MHz telemetry. So the data rate is not as efficient as using like a 5 GHz telemetry. Can send more data over wirelessly. While it is still customizable, it is inflexible because of some of the components that is sort of fixed into the ecosystem. So hence we have a solution for that. So next slide is regarding our solution. And as you can see here, all the drone operator has to do is just to input the target location, and that will generate the cluster and the spiral, and the drone will fly with respect to that spiral. So when it detects the phone here, it will actually send that information into the user interface, and that is quite useful for the first responders because they can see in real time that, hey, perhaps there is a casualty there. And more information can be seen here, which is regarding the drone ID, so we know which drone we are tracking. We also know the lag and long, and also landing and disconnecting the onboard computer in case we want to debug the problem with respect to the drone. So we thank you for your time. However, next we'll go on to the poster. So for the poster, we want to highlight 3 main components. So the first component is actually the sensor with the directional waveguide that's running the signal processing algorithm, and it's doing some Bayesian. And the second component is the Bayesian pathfinding for faster search. So it allows both adaptive and naive traversal. And lastly is towards visualization, which is about the simulated environment in gazebo and mission control graphical user interface. So I just want to take this time to thank our academic mentor, Prof. Malika for help, and our industry mentor, Jonathan, for his assistance, and Prof. Willett for his assistance throughout the signal processing stuff, and Patrick for his help for the communication side of things. Yeah, thank you.
Show video.
I think it's very impressive how the team has come a long way since the first presentation, the first iteration.
Yeah.
There's a lot of good details that they've gone through in terms of the engineering study and trade-off studies.
Absolutely, absolutely. Thank you so much. I think we're going to show a quick video for the demo. Are we?
Oh, is this one?
Is this one?
the one that
Yeah, we showed on it. Okay, okay. Then, okay, then we will do Q&A now. So Jonathan and, sorry, you guys want to start off with the questions? Okay, great, good.
What was your biggest challenge since the first iteration to now? Was it hardware, software, integration?
Both.
I think maybe we start with the sensor. Maybe Ivan can shed
All
some light
common
on.
center so that we
Maybe
can,
one per area.
Maybe actually can share our sensor.
but all be in view so that you're in the camera view.
Okay, so developing the sensor was one of the major challenges we faced in completing this project, right? Because for half the time of this capsule project, right, we were analyzing signals in the time domain, which proved to be quite fruitless because given the high frequency of the RF signals, right, we cannot capture any noticeable change in the signal in order to accurately quantify that there is an active communication channel there. Hence, we had to make the swap to the HEC-RF1 SDR to use fast Fourier transform, so we can do processing the frequency domain. So that actually allows us to see the contributions of the different frequency components when we detect a signal, for example. So that thing is a lot more noticeable, and therefore it's much more efficient in educating the data that we require for signal discrimination. Yeah, so that's major challenge number one.
And maybe just to add on, I think it will also show about how it also involves both the software and the hardware side of the challenges. Means that beyond just the hardware, you can see in the next slide was how can we process the data. So it's about how do we make sense of the waveform that is forming and all the data. So and I think this again was also asking us about if you wanted to we must also be aware of how much computing power we have, because just has limited power. So initially, when we try to sweep a very detailed waveform, it's actually taking a lot of time, and it's a lot of data to process at the same time. So we had to actually even like try and error, try to find a sweet spot to see what is the, how often should we sweep, what is the bandwidth we are sweeping at, and also how it can be quickly be processed. And we also try out different kind of unsupervised machine learning methods is to, I think for us to experiment and explore which one performs the best. And I think one of the highlights we want to talk about for HDB scan is the fact that it doesn't require us to pre-specify how many clusters or how much to differentiate. Because a lot of the previous methods require you to predetermine I need how many clusters, but in this case you can see that if there's all noise, they won't consider it as a cluster, but if there is a significant group of data points that's above from the rest of the points, then you can see that as a separate cluster. So this is a very important characteristics that we were looking for, so that took us a few trial and error to identify. So I think the sensor is a very interesting component which requires both the hardware and the software coming together. Yeah, other challenges you want to talk about?
Maybe I can share a bit about pathfinding. So if you look at pathfinding, it seems kind of idealistic. We're using some naive adaptive travel, so but this actually doesn't look so nice in real life. We have to account for drift, we have to account for how fast the drone moves, can it go such an angle. These were things that we thought about, but we weren't sure what would happen in practice. So when we did our field trials, we did have to account for that and add different checks like can we adjust the angle of movement, can we look at how fast it moves, how slowly, is there hyperparameters that we can change in terms of adjusting the algorithm so that it works in real life. Yeah.
So in terms of testing, we had problems with localization because our drone originally heavily relies on GPS, and because the drone arena is an enclosed area, the GPS doesn't work well. We tested if it's a GPS problem, but so we found that it is because of the aerial arena, because we flew it in Marina Barrage to test the GPS and it was fine. Yeah, so thankfully we managed to, the Trust Lab has a built-in RTK antenna in the top of level 7. So we tested it out and we managed to get like pretty good localization as well.
Yeah, maybe I elaborate more. So the RTK antenna is basically sending GPS or GNSS corrections to your GPS, because then GPS is not as accurate. So this antenna is actually located outside of SUTD, and that line outside with your drone with the F90 RTK GPS is able to compute all the differences, and then it's able to give a much more higher localization capability of the drone. So another thing that I want to discuss is actually some of the communications side of things. For example, initially when we wanted to run the ROS messages over to the drone, the ROS stack, we wanted to use PTPD, so it's a point-to-point protocol daemon. And however, the problem with that is that when we try to use it, it's sought to like interfere with the communications, and hence we opted to use the SUTD drone arena Wi-Fi to send the communication over, and we find that it works sort of better.
Great. I'm pleased that you had to go through the challenges, especially for the GPS accuracy, because in real life, your GPS will not be so good. So it forces the team to find alternatives, like we maybe have to put an RTK antenna somewhere higher, on higher ground. So whether it's intentional or not, the SUTD drone cage GPS degradation actually is really good for drone teams, I feel. It doesn't give you the ideal world state, which is what you're really designing for.
Just to add on, so everyone have like a piece of like the sensor, the drone, then like every single or part of all have like the challenges. But the biggest challenge I think is like in how we integrate all the components together. Like when we put everything into the drone arena like this, when we do all the bench testings on the Jetson, on the battery, on like the power plug, everything working fine. But when the drone starts to fly, then you have all the system running on the same onboard computer, and when it's on battery, then we start to have a lot of problems. So this video, we actually only managed to capture it last night, with like very last minute. We spent days after day trying to integrate everything together. Sometimes it rains, sometimes there will be a bug, no battery or something.
Yeah.
So yeah, the integration is also one big challenge.
Especially for real life, so even in the working world, worry is the night before then it's started. Well, praying.
So what was the main problem that you faced before that last night? What was the main issues?
So we have a few integration steps. We first tested with like this QDC baseline, which like just control the drone with by sending like latitude and longitude based on this. Then we convert over using our own mission control. Then for this, that means we need to integrate our own search algorithm inside, and we have our own communication link. So the communication link when you use telemetry is very weak. So we switch over to using the Wi-Fi 5 GHz. Yeah, and with that we had to try out a few different ways to set up the Wi-Fi. We brought our own router. We tried to set up the own network, but that wasn't strong enough. Then finally, thanks to Prof. Shawway, we got like the Wi-Fi password for the drone arena. So we used that one and managed to send all the data over to the Wi-Fi. That also explains how we can get a very nice, like tracing of the drone right here. Yeah. And last night is like our final step in the integration. We try to have a real-time detection shown here. Yeah. So yeah, you can see like you have one phone here, then another phone here. Then as the drone cover, you will spot like two detection. Yeah. So that's what we try to show you guys later at 11:30. Yeah.
So you're just gonna yeah. So the Q-bell control one that he mentioned earlier was direct to the flight controller, but for our system we needed to arbitrate everything through the onboard computer, which posed more issues in terms of simulation as well as transferring from simulation over to the physical implementation.
So now you have the first like working prototype, everything's working. Right? So what do you think will be the main improvement you would want to make if you were to continue the project?
I think one of the biggest problem that we've seen so far is how can we get like a very sensitive like sensor detection. So when I've been doing this, he need to manage the threshold a lot, and depend on the noise of the environment, he need to like either raise or lower the threshold. So that's one thing that we maybe can use some smart algorithm to, how to detect the threshold in this like a manual demonstration. Yeah.
And then just to add on, I think in the real world scenario, we can use more than one detection mechanism, because I think we can understand it as the sources of information. If you're just relying on one particular source of information, it could be limited. So we think that if further development could be added on more detection mechanism, but we think that as for the scope of our project, with the time that we have, we wanted to do something that is more novel, and so that's why we limited it to just the Wi-Fi detection. So if we have more time and more scope, then we might want to involve with like maybe computer vision, infrared, or other kind of detection mechanism to maybe form a better like understanding. Yeah.
Do you want to upsize the drone?
Yeah. Multi-drones?
So I think for multi-drone system, so I think we worked really well that we could have the simulator working with multiple drones. But I think in real life we were facing some challenges regarding multiple drones flying together. At the same time, I think there is also safety concerns regarding, because I think the drone operator had to manually take over, especially even flying this current drone, one drone. The manual takeover is a very important feature, and it is it's usually quite taxing for the drone pilot to be very focused, make sure that everything is safe. Yeah, so to fly multiple drones at the same time, I think we might also need a bigger team to handle all of these maybe physical constraints that we are facing. Yeah, so I think maybe a more physical demonstration of multiple drones would be something that we want to achieve, but at least on the simulator, theoretically, will handle multiple drones. Yeah.
And you want to say about ROS too?
Sorry, what's specifically about?
I mean, that's the latest industry standard. So far, like this is recently released. Like for ROS 1 used to be the standard of industry and academia, and ROS 2 is the latest one. And people like this is a skill. Like, I mean, people are going for to make sure like all their newer system works with it, because all the older packages there was no more work on the ROS 2 domain. So they've actually done it with the latest and the best package system. So that's really good. And it allows you to do a high fidelity conversion from simulator to physical world. The gap is very little. Like they can literally create high fidelity models of the drone into the simulator, and all of this can be transferred into the physical world. So that's one of the biggest trends.
We've been waiting for people to go on ROS 2.
Exactly. Yeah. It's a big thing for
It's been
robotics
around,
lab.
but-
Yeah. We have some dinosaur code as well from ROS 1. We have to do it someday. Any questions, Jonathan?
Very good. I think it's good. It's very good effort by the team.
I think the team is big, but I think when the team is big, it also brings complexity to the project, which probably is needed. And it's good that in the end you'll be working come together because midterm was still very when we saw the demo during the midterm, it's still a little bit far from what we see. So a lot of work has been done in the past few weeks to reach this stage. Good job.
So yeah, I want to congratulate you all. I think you guys have worked beautifully well with each other and worked with each other's strengths, and that has got you so far. So I just want to wish you all very best for the next stage. I'm very excited for the project to come out. Please write the paper.
What will the paper be on? The whole system or?
Yeah, the whole system, the sensor itself, field trials that they have done, and potentially putting it into a multi-drone setup. That can be explored.
Do you have a GitHub for your code base?
Oh, very big.
Yeah, I guess all the different packages.
So you can also have a project page from the GitHub to keep it as a portfolio.
We actually have a MASNRD project page, so all the repos are
Okay, great.
See, they
just
have,
transfer the organization over. Okay.
and all their prints are also with MASNRD.
Your own branding.
We have a technical blog at DSTA. We'll be happy to feature the project. I think it's a lot of good effort done.
That would be much.
Thank you.
So, all
Any
right.
questions for us?
Yeah, you guys can join us when we set up the live demo.
Yeah, we'll be around. So I hope you all learn a lot. I think so beyond that, the algorithms and integration, the way you all handle any conflict resolution or disagreement or debugging, right? That will take you through your careers down the road. The spirit of not giving up and pushing through to the last day, you will, that will be continued. That's a very good spirit to carry on as you start your careers. Thank you.
Thank you.
How narrow it is? How wide is the angle of detection? Okay, now is it below?
Should be. Yeah.
Oh wait, detection.
There's a hit.
Yay! Yay!
Yeah, I got detection.
Whoa! Well
Oh,
done.
okay, the person icon.
No, it's not.
Well done, guys. Oh, yay!
On the screen.
Show me happy faces.